Welcome back to the 21st video about the full fly-by-wire electric outboard project. In the previous video, we calibrated and tested our new noise-reduced circuitry, and the results were generally good, but for two issues. First, more an annoyance, the noise level on our battery voltage channel increased when we reached the upper limit of our voltage range. The second issue was a real problem, because when we reached that upper voltage range, we also saw a significant crosstalk from the voltage channel to the current channel. Card here. Link in the description. Today we will try to solve at least the latter, more pressing problem. And as you can see, the oscilloscope will come out to play again. Enjoy! Our first, let's call it issue, is that when we increase our battery, that is supply voltage, from 20 volts to 29 volts, we see an increase in noise. For the raw ADC values, the noise more than doubles. And for the oversampled values, the noise almost doubles. And I explained that away with our switched regulator, somehow changing mode when we increase the supply, respectively battery voltage. Our second problem, and that's a real problem, is that our current readings seem to be influenced by our supply voltage. We are currently at 15 volts, and according to my lab supply here, we are just consuming 45 milliamps. And yeah, this looks good, but if we increase the voltage, you see the consumed current goes down, but our current readings go up. So till 20 volts or so, it's, well, okay. But if we go even higher, we come here into a region where it's almost constant. 26 volts. 28 volts, and you see, oh, we make a big jump here. We make a big jump here. Okay. This is not good. So we go from 0.8 to about 0.08 to about 0.2 amps. And if I go to 29 volts, we double again to, more than double, to about 0.4244 amps. And yeah, that's a no-go. That's really a no-go. Let's tackle the latter problem first, because it's really a problem and not just an annoyance. The first question we could ask is that some kind of crosstalk between our voltage channel and our current channel, that is between the op-amps or inside the ADC, or is that really a supply voltage problem? Something's not really working here with our supply voltage and our reference voltage as we ramp up the input voltage to our circuit. To answer that question, we can simply disconnect our voltage channel from the supply voltage coming in, and we put that somewhere safe here, our 15 to 29 volts, and then our voltage channel stays at a constant voltage. It should display something near 15 volts, because that's now our zero for the ADC output. We start at 15 volts again, and our voltage reading here should stay at 15.12. That's our 0 point. As before, we have 0.06 amps here, and if we ramp up the voltage slowly but surely, we see Nothing happening. 25, 26, 27, 29. Okay. We have crosstalk. I hope for something more trivial, but it is what it is. Now that we know it's not a power supply issue, let's home in on the ADC circuitry. And first I want to test if we have some crosstalk between the different op-amps in my quad op-amp package. There shouldn't be any noticeable crosstalk. The datasheet promises us, yes, channel separation of over 900 decibels, so a factor of over 10,000. But anyway, let's test that. For that, I will reconnect our battery voltage input here to the voltage channel so we can have some crosstalk. And I will monitor the output voltage of the op-amp for the current channel going in our ADC. Please note that output here has about 50 millivolts per amp. So if we see a change of 100 milliamp here in the readings, that should give us a voltage change of about 5 millivolts. So I reconnected the battery voltage input to the voltage channel. And I connected my multimeter probes here to the ground pin of the op-amp and the input pin on the ADC for our current channel. Okay, what we're seeing here is kinda flabbergasting. Okay, so you see my amp readings are now negative. They were 0 before I changed the code, so I can actually print negative readings. Yeah, we are at 1.253 volts input voltage to our ADC on our current channel. And that stays basically rock steady as I'm decreasing here the voltage. And now we have the different effect. Now I go down with the voltage and our current readings increase a little bit. Even though our input voltage stays within, measurement accuracy, constant within 1 millivolt. I don't know what to say. Okay, let me show you something else. We are currently at, you see it obviously there. I'm not sitting in front of the notebook, obviously. 16 volt supply, and we're reading 0.05, 0.06 milliamps. And I just have here my multimeter probe, and I'm sticking that now here in to the ADC's current input, and we'll suddenly see a jump in the values. How's that? Obviously, there's something going on that you can't see on a multimeter, and it has something to do with a capacitance again. Instead of the multimeter, I connected now my oscilloscope here to the op-amp ground and its output to the ADC's current channel. Obviously, our op-amp likes the oscilloscope probe slightly better. We're still off, but not, crazy. What we're currently seeing on the oscilloscope is that we have here some peaks going down with an amplitude of, the oscilloscope says peak to peak 500-600 millivolts. My cursors, I said, say, where's the delta? 420 millivolts. And they are at a frequency of 2.5 kilohertz. which is, of course, our sampling frequency. Anyways, let's zoom in a little bit here. So, the cursor here on the x-axis, you can see that, yeah, that's our sampling time at 1.5 cycles, 2 megahertz. That's about 750 nanoseconds or 0.75 microseconds. And as you can see, the voltage during the sampling is crashing down quite a lot, and it recovers at the end of the cycle, of the sampling cycle, to the normal value, but yeah, it doesn't look too good. Now let's increase the voltage then, shall we? So 16 volts, and you can see it over there. If something drastically changes. No, not really. I mean, my readings obviously change. Okay, 29 volts. And have you seen that? It jitters every now and then. Interesting. And also, it went a little bit up here and doesn't recover to the, let's say, idle voltage completely during the sampling. Interesting effect. Let's go down to 15 volts again, if that looks any better. Yeah, that looks again slightly better. It's really hard to make out on the oscilloscope, but yeah, that doesn't look good at all. We had a similar problem in video number 10, where we implemented the water intrusion detection circuit. Card here, link in the description. The thing is that our MCP3204 DAC, as soon as we sample, closes that switch here internally, which is connected via approximately a 1 kilo ohm resistance to our sample capacitor of 20 picofarads. And our OpAmp, which is feeding into our DAC, sees suddenly a change in the load. And obviously it cannot react fast enough, and so we see a sharp drop in the output voltage, which only slowly recovers. The 7 picofarads here of internal capacitance at the pin are irrelevant here, because they are constantly connected to the output of our OpAmp. So how did we solve that problem back then? The 500K resistor up to Vref in our water intrusion detection circuit was also not able to charge up the 20 picofarad sampling capacitor in our ADC fast enough. And so we added a buffer capacitor that is much larger than the sampling capacitor and basically buffers that sudden change in load here. But we also know from video 19, where we chased noise and intermittent errors, card here, link in the description, that putting a large capacitive load at the output of an OpAmp can make it oscillate. In our case, we had a 100 nanofarad capacitor here at the output of our buffer OpAmp for Vref, and that thing oscillated like crazy. However, if we look, for example, at the Texas Instruments buffer OpAmp to ADC circuit collection, an application report, link in the description, we find a circuit like that, where between our OpAmp and the input of our analog to digital converter, there is an RC element. So a buffer capacitor at the input of our analog to digital converter, but it's decoupled from the op-amp output by a resistor. And you can look at each and every schematic in that application note. There is always an RC element at the inputs of the analog to digital converter. And Texas Instruments is not alone in that. You find application notes from other vendors that suggest exactly the same. Anyway, in the text below that figure, it only says resistors R5 and capacitors C2 are ADC compensation components. In the description of another circuit, it's stated R5 and C2 are compensation components specified by the ADC datasheet. Also not really helpful. Fortunately, there is a paper from Analog Devices by Alan Walsh that goes into the details of designing that RC element. Link in the description. It talks specifically about that kick we observed on the oscilloscope. Unfortunately, the math in the paper is based on sinusoidal signals as input. Nyeh. And believe me, there is really a whole lot of math involved in that. Anyway, in the example given in the paper, you end up with a relatively small capacitor here, 2.7 nanofarads, which is still 2 orders of magnitude larger than your sampling capacitor, and a relatively small resistor in front of it. And I've seen in many other circuits and many other examples similar values, but always for sinusoidal input signals. But fear not, I have a second calculation method for the RC element for you. This time from Texas Instruments by Tim Green and Art K on YouTube of all things. Link in the description. It of course covers exactly the same problem, but takes a completely different approach and talks mostly about charges and tau constants. It also involves a lot of math, about 24 equations, and in addition you should optimize everything afterwards with some simulations. That last method, besides being quite complicated, also didn't quite fit for our application. You see, it assumes that you are sampling as fast as you can with your ADC. We have a rather long interval between samples, currently set in the software to 380 microseconds. And the switch inside the ADC to charge the sample capacitor is only closed for 0.75 microseconds. That is 1.5 cycles at our current SPI clock speed of 2 megahertz. That is, even if we assume the worst case, that is, we have to charge up our external capacitor from 0 volts to the full reference voltage of 2.5 volts, we basically have all the time in the world to do that. And of course, we will have at the end a little charge error. And then, when the switch closes, our sample capacitor is mainly charged up from our external capacitor. And of course we will see, not to scale here, neither the time scale, a little drop here, so a little discharge error. But this is probably quite small because at the same time as the external capacitor is supplying charge to our sample capacitor, the op-amp is still also supplying current here. So here's my math, and I'm not claiming that it is totally correct or complete. Anyway, we already talked about our interval between samples, t interval, which is 380 microseconds, and our sampling time, t sample, which is 0.75 microseconds. Yeah, number of cycles, the switch is open, divided by our SPI frequency of 2 megahertz. Then we have our charge time, the time we have to charge up our external capacitor. That's simply the interval between samples minus the sample time itself. That leaves us with 379.25 microseconds. Our ADC resolution is 4096 LSBs, and I want my end of charge error to be 0.1 LSBs. Worst case, going from 0 to 2.5 volts. That is in decimal numbers, not LSBs. 0.000244 epsilon charge, that is our charge error in LSBs, 0.1, divided by our resolution. Now, the number of taus, you remember tau, the RC constant, tau equals R times C. We need to get to that error, to that small error, is the logarithm from 1 divided by the error we are willing to accept. In our case here, that turns out to be 10.6 times tau. That is, for the time tau, our RC constant, we have our charge time available, T charge, divided by the numbers of tau intervals we have to fit into it. And that works out to 35.71 microseconds. Okay. Now for the discharge error, when the switch closes inside the ADC, I've given us 0.5 LSB. Yeah, the industry standard, it seems. In decimal terms again, so the discharge error in LSBs divided by the resolution in LSBs, we end up with 0.00012221. So our epsilon discharge. Our sample capacitor is 20 picofarads. And now I kind of guesstimate our external capacitor as simply the sample capacitor divided by the discharge error we are willing to accept. That's a rough estimation. It doesn't take into account the internal input resistance of the ADC, nor the additional current we get from our op-amp. But it works out as 164 nanofarads. That's quite a lot. Then we need, of course, still our external resistor. And yeah, I told you tau is equal to R times C. So R is equal to tau divided by C. So we simply take the tau we already calculated here and divide that by our C external. And that works out to 280 ohms. And I'm quite nervous about these values because that is a real huge capacitive load on the output of our amp, even if it is decoupled by a, let's say, 220 ohm resistor. We'll see. I ended up the next smaller capacitor value I had because I'm still afraid that our op-amp starts oscillating. That's 150 nanofarads. And here you see now that 220 ohm resistor from the output of our op-amp going to the ADC input for the current channel. And now let me reconnect the oscilloscope probe, and we'll have a look what that does for us. Okay, so far so good. We are at 15 volts, and yeah, on the oscilloscope you see it's the same setting as before, absolutely nothing. Let me change the time scale a bit. Maybe we are overlooking some oscillations. No, just noise. Wonderful. Yeah, as I mentioned, I was, and you see a little here. I was afraid that we get some oscillations from the op-amp again. But the real question is our crosstalk done now? We are at 15 volts, so 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. No crosstalk. I mean, you can't see it, but of course the current consumed by our circuit also went a little bit down, and that exactly was reflected in the readings. So perfect. And while we're at it, let's have a look at the voltage channel. Let me move the oscilloscope probe over to it. Okay, don't make a short here. And as you can see on the scope, we see nothing. Okay, we are completely out of range. Let me turn down the supply voltage again. There we come. There it is. There's our voltage signal. And yeah, it's basically exactly the same effect that we saw on the current channel. So let me add that RC element to our voltage channel 2. And here it is, a 220 ohm resistor going from the op-amp output to the voltage input of our ADC, and another 150 picofarad capacitor to ground. Now let's reconnect the oscilloscope probe to the voltage channel. No shorts, please. Okay. And let's have a look-see. And here we are. Our voltage channel is also clean. For our voltages, yeah, I guess so. No problems whatsoever. Perfect. But wait, you ask. How could that problem possibly cause crosstalk between the voltage and the current channel? Well, the main problem we saw was that our op-amp had not enough juice to really drive our sample capacitor inside the ADC high enough, fast enough, or let's say to the real output voltage we want fast enough. And we sample all our channels one after the other in short succession. We only have that long interval between our bursts of samples of our 4 channels. And therefore any residual charge in that sampling capacitor will have some influence on the next channel sampled if, our drive circuit is not strong enough. And that's obviously what happens. At least that's what I think that happens. Add in some large capacitive coupling between the channels via my breadboard, and there you have it. That's it for today. Quite an unexpected problem caused, but I think our solution works beautifully. I will do another calibration of the whole thing now off camera, and we'll show you the results next week. Till then, bye.